Hello there. Today we'll be doing matrix search sequels. Given a two-dimensional integer matrix where every row and column is sorted in ascending order, return whether an integer target exists in the matrix. This should be done in O of n plus m time. So O of n being the number of rows, and m being the number of columns. So that is 6 in this example 1. In 6 moves, we should be able to find our item because there are 3 rows and 3 columns. So output is true, and that's all because the 7 was found here. So we have 3 ways of solving this. We can do a O of n times m. This would be the easiest way for us to code, but most trivial way. We have a O of n log, O of m. O of n, O of n log m. That would be a binary search of every single row where the target is within the range. And then there is n plus m time, where we will start at the top right-hand corner of the first row and move to the next row if the item is smaller, or move to the previous column if it is bigger than the target. The item is bigger than the target. Well, the reason why we know this method will work is because we know that the item must, if it's less than our first item, it must be in the previous column. The reason being, it's because all the items in this column must be less than this particular item here, because this is sorted in ascending order in every row and column. So as you can see, this is ascending order, this is ascending order, this is ascending order, this is ascending order, this is ascending order. So in all directions, it's always going to be ascending order. And knowing that if it is lesser than 9, it must be in previous column. If it is greater than 3, then we can keep going, 5, and then 7, and we find 7. If suppose we were looking for a 2, then the 3 would return another row, and we would go down and find the 2. And so we will always find our target if it is in the proper row and column. And so let's start with coding the least functional method and move towards the most efficient method. So for row in matrix, if target in row, return true. Otherwise, return false. All right, let's run it. And submit. We have a pretty good solution here already. Let's speed it up. Let's do that binary search. So let's define the binary search. This is our helper function, bsearch. Let's put it in here in the solution class. And let's do it. So low is going to be and high. Well, that's going to be 0, and high is going to be lang row -1. Following, while low is less than or equal to high, mid is equal to, I think, well, we don't know how big these numbers will be, so we're going to do a safe method of getting our mid. This is low plus high minus low divided by 2. So if the row of mid is equal to target, return true. Else if row of mid is like less than the target, that means we are in the wrong place and we need to move the low higher to be equal to mid plus 1, eliminating the items that are smaller than the target. Else, we're going to set the high to be mid -1 because we're going to eliminate everything that was bigger than the target. Otherwise, we don't find it, we'll return false. Once that is done, we can do a for row in matrix again. And if row of 0 is less than or equal to target, and the row of the last item is greater than or equal to target, within range. So the row of 0 is less than the target, and the target is less, well, the row of 1 is bigger than the target. The last item in the row is bigger than the target. If self.found row and target, return true. Return false otherwise. So let's run this. Oh, we have an error. Found, oh shoot, search. So perfect. This is a very fast solution already. This might be actually faster than n plus m time, depending how big our number of m's are. So yes, because log and m times, when you have a log, is always going to be pretty small. But let's do n plus m time just to complete this. All right, well, I'll leave this here in the background. Just shift it down all the way down to below, and comment it out. Okay, this method requires us to start at the top right-hand corner, and so let's do this. So row and column. Let's get the row and column, n and m. That is the row. Number of rows, and n is number of columns. Yeah, so row, column, 0, and column is n minus 1. Then while the row is greater than 0, and the column is greater than or equal to 0, and the row is less than the length of the number of rows, and the column is less than the number of columns, then we can continue checking. So if the matrix of the row and column is equal to a target, we will return true. And else if the matrix of the row and column is less than the target, we will then move down to the next row, because you can only find something bigger if we move down to the next row. Otherwise, it's smaller, then we will move back one row, one column to find something smaller. If we don't find it, let's return false. We have an error. Solve, we deleted that. So let's run that. Perfect. Very good. Of course, this happens to be a little bit slower, maybe because due to some m being extremely large. Well, it looks like it's only up to 250 here, but I mean that's 250 versus 8 times n. So anyways, I think that is a pretty good explanation. Let me review. So today we went over 3 methods, O of n times n, which was acceptable apparently. I think it was because it was partially because I think we had a binary search more or less built in. Then we created our own binary search and removed items that were out of range. And lastly, we did a O of n plus m time, which we see here. The reason why it works is because we eliminate the numbers that are going to be smaller by going to the next row and looking for a bigger item. And we eliminate bigger items by going to the previous column, and because doing so is always going to be in order. Well, that's all for my explanation. If you have any questions or comment, please offer them below. And if you enjoyed the video, like and subscribe. And if you want more content, please check out the description for my link. And have a nice day.